now account for that hill, and that's where I'm struggling. Do we subtract whatever that hill would be from this equation or something, or it almost looks that way?
Yeah, well, I guess I would, let me put it in these words. What you just said, you said that we have the equations if the hill wasn't there.
Right.
Okay, I'm going to change that. I do agree it's the equation if the hill isn't there. I would say, though, it's an equation for the entire motion, whether the hill is there or not. In other words, you have one equation for x that depends on time, and you have another equation for y that depends on time.
Right.
Okay, so all you have to do is you could, irrespective of the hill, you could say, where is it after 1 second? And you could just put in 1 second, and that would give you the x and y coordinates after 1 second.
Right.
Okay.
Okay.
You could put you could put in 2 seconds, and then you would have the x and y coordinates of 2 seconds.
Right.
Okay. So I think a better way to describe those equations is I have an equation that lists the position of it as a function of time.
Okay. All right.
Because you could give me any time. Now, granted, if you gave me a time that was so big, it would have already hit the hill. So I need to be a little bit careful with that.
Right.
But for the sake of discussion, let's just say it takes 3 seconds before it hits the hill. Okay. And we don't know what that is. But again, just bear with me for a second. That means you could give me any time less than 3 seconds. 1 second, 2 seconds, a second and a half, 1.7 seconds. I could put it into those equations, and I can get the XY coordinate of it.
Okay.
Okay. So keep that in mind. That's really what that is. Okay. So as you said, I really, at this point, I'm not doing anything different, whether there's a hill there or not.
Right.
Okay. Now, so here's the part where the hill comes into play. The hill comes into play then is I need some kind of mathematical equation that connects the x and y of the hill with the x and y of the projectile.
Okay.
Okay. So I'm wondering if I should turn on my camera here. Maybe this would be a good time to do that and kind of say, okay, what would an equation for the hill look like? Connect my phone here. There we go. Come on, can you get my face in here? There we go. Can't get my face in front of it. Okay, finally got it unlocked. And hang on for a second. I thought I turned it so it wouldn't go to sleep, and it was asleep. Yes, I didn't. So let me go to never. Otherwise, we're going to run into troubles. Okay. Okay. Okay, so at this point, you have, and at the risk of boring you too much, I'm going to say you have one equation that says x equals, and it would really come out to be this, the initial velocity times cosine of the angle times t.
Right.
And okay, the other equation would be y equals, and you would have initial velocity sine of theta t minus, and it would be 1/2 of 9.8. So I'm going to put 4.9 t squared.
Right.
All right. So that again is an equation that says this, that you give me any time, like 1 second, boom, it tells me where it is. Here's x, here's y. You give me 2 seconds, and there it is. You give me 3 seconds, something like this. All right. So I would say then the next thing I want is what's the equation for a hill? So maybe I'll just draw another hill. If I remember right, and I guess I could go back, wasn't that 20 degrees?
20 degrees, yes.
Yeah, okay. So what I could do then is say, okay, it's going to land somewhere on the hill.
Right.
Okay. All right. So let's call that X and Y. And that would be represented by this formula here. There's the X and there's the Y. Okay.
Right.
But then I would do something like this. I would say, all right, let me look at the function. Let's do cosine first. Cosine of 20 degrees. And as long as I'm here, I'm also going to look at the sine of 20 degrees. See, the cosine of 20 degrees is the horizontal distance, x, over the hypotenuse, and that's the point of the problem, d.
Right.
So I'd write that as x over d.
Right.
And then sine of 20 degrees would be this vertical distance. So y over d. And that means I have an equation that represents the hill.
Right.
Okay, in terms of x and in terms of y.
Mm-hmm.
All right, and what I want is this equation for x and y that represents the hill to be the same x and y that represent the projectile. That's where they cross. That's where they hit.
Right. Okay. Right.
So I'm going to take this x and put it into here. So
Okay.
when I do that, I have d cosine 20 degrees is equal then to initial velocity cosine theta times t.
Mm-hmm.
And if I do that same thing for the y here, I would get d sine of 20 degrees equals initial velocity sine of theta t minus 4.9 t squared. And I got the impression that's where you were struggling. I'll keep going, but you were.
No, if I'm not mistaken, all we have to do here is find t and we'll have what we need.
Yeah, so right at this point, we know the initial velocity, and I believe the firing angle was 40 degrees.
Yes.
Do you remember what the initial one is, or should I go back and look?
But the initial velocity?
Yeah.
98.3 meters per second.
98.3. Okay. But again, let me know how far in the math you want me to go. But by putting those in here, I have an equation that has just two unknowns in it.
Right. And you have two equations.
And two equations. So
okay.
I would solve one of them for probably t.
Right.
And put it into the other one. So then I would have just one equation with a d in it.
Right.
That I can then solve for d, which is the,
No. Right. Yeah. No, I think that really helps. Now I couldn't. Now I have them tied together now.
Yeah.
I'm just finding a common time where they hit, and from that you can find the distance.
Right. And to me, I if I'm understanding your hang up, your hang up was really right here is how I would describe it. You have an equation for x and y of the projectile.
Right.
And you also then need an equation for x and y of the hill, and then set them equal, because that's where they meet, when the hill meets the projectile.
Yes. And you do that through finding the time, then you get your distance.
Yeah, right.
Okay, I just somehow wasn't making that connection there. So
Good.
Great, thank you very much.
Uh-huh. All right. Good question there for your 121 crowd. Hey, I'll say it again. Is there a 102 out there? Hunter, you oh, that's not Hunter, you're 123. I see your question. You say when the 102s are over, yeah. But we haven't had any 102 quite yet. I'm kind of anticipating that though. They've got a test coming up this week. But that's fine. All right, so I'm going to go back to the top here and go to the question. Let me tear this one off here. So let's go to Anthony, who asked for number 40. All right. All right, and looks like a couple more people came in while I was chatting with Ed there on the 121. Let me emphasize, if you're in a 102, you got priority right now. So just send that up and we'll do yours next. So, but meanwhile, let me write down here, chapter 19, number 40. I'll even put that here on my notes. So that's a 123, chapter 19, number 40, and we'll be starting it at 10:20 here. All right, so let me re-share my screen. You guys can see my phone here. Oh, I got to reconnect. It's circling here. All righty, looks like it came through. All right, nice. All right, now let me find you guys in 123. Let me find your questions. Here we go. 123, chapter 18, and this must be chapter 19. Yeah, going down to number 40. Oh, it's a big number. Anthony, you always ask me the hard ones, don't you? Oh, look how long it is. All right. You always...
I honestly just need like part A, because if I have part A and part B, I could do the rest.
Oh, okay. Yeah. And okay. I get that. Yeah, I was reading this one this morning. I said, oh, yeah, this is a long one here. But let me just read it here. A bimetal strip is made out of two ribbons of different materials bonded together. Okay, now they have a picture of it down at the bottom and also in the book. And I think I did our bimetal strip in the lecture video, I hope. And but it's basically made out of two metals. And it starts off by saying, first assume that the strips are originally straight. All right, so here they are. I'll just say they're at room temperature. So who knows if it's around 20 degrees here. But the strips are warmed, and the metal with the greater coefficient of expansion is going to expand more than the others, forcing them into an arc. So what will happen is it will look something more like this. If they're bonded together, and they remain bonded, because it's quite possible you heat them and they just, aren't connected together anymore. But assuming they're bonded pretty tightly, and they can handle the stress and the bending, one is going to be longer than the other one. So we've got a long one and we got a short one because they expand different. And that actually makes an arc, which they say would form part of a circle of radius theta. And they do a good job in their picture. They're saying, okay, take the inner one to be radius 1 and the outer one to be radius 2. So the longer one clearly has to be on the outside, where the length is a little bit longer here. And so in terms of the lecture part, maybe I better go back and see what they're after in this question. Warmed, forcing the strip to make an arc with the outer radius having the greater circumference. Derive an expression for the angle theta as a function of the initial length of the strips, the average coefficient of linear expansion, the change in temperature, and the separation of their centers. So basically how thick the pieces of metal are. All right, so I would say this, that let me take this one that is going to expand the most, the one that's going to be on the outside, the one that has radius 2. Let me call it original length L2. And the shorter one, let me call its original length L1. Now, I got to be careful saying shorter because it's shorter after it warms up. It's not shorter at the beginning. At the beginning, they're the same length. So my poor notation here should probably look like this. How about initial length? And they're both initial length. But when they warm up, this outer one becomes L2, and the inner one, the shorter one, becomes L1. Maybe that would be a little more clear in my mind. That, okay, they have the same length to start, and then they warm up. And the outer one is longer than the inner one, so I'll call it 2 and 1 to match the radius 2 and 1. But here's the kind of the two pieces of this puzzle that come to my mind first. The first one has to do with the chapter, the thermal expansion, because we learned that the growth, that is the delta L, is equal to the alpha L delta T, where L is the original length. So if I apply this idea to this problem, I guess I would say something like this. L1, so the shorter one, would be alpha 1 times the initial length times delta T plus the original length. And so let me just kind of, explain my math here. This right here is how much it grew by. And so number 1 has an original length and alpha 1, and we increase its temperature and it grows by this much. And it already had this much length. So when you add the two together, you get the new length. And I could say the same thing with L2. It would be alpha 2, L initial, delta T, and I could add to its initial length. Okay. So that's the idea of this chapter, or one of the ideas of this chapter, thermal expansion. Okay, so there's our thermal expansion. But let me also, at the same time, and see if I can fit it right next to it. I'll just kind of split my paper. So right next to it, I can do some geometry. And I'm going to remind you of the same geometry did we do this with waves? I think we did. That an arc length would be, if you have an arc and you say the arc length is S and the angle is theta and the radius is R, then the arc length is theta times R. Yeah,
we did that in like 1 or 2 problems, I think, in last chapter.
Yeah. Okay. So, yeah, so I guess I'm saying we saw this already this semester. I know you saw it a lot in 121 when you did rotational motion, but just in case you've forgotten that geometry, this comes from the Greeks. This is how the Greeks defined an angle. They said the angle was the arc length divided by its radius. That's why a full circle comes out to be 2 pi. So that's another way of saying this only works if you're talking about the angle measured in radians. So keep that in mind. But I'm going to use that property of arc length and radius to this problem because, you see, I have an angle that they want me to find, and I have an arc length, which is the length of the rod, and a radius. And so that's kind of the perfect recipe for this. And so I guess I would say this, that L1 is the arc length of the smaller one, so it would be theta times R1. And L2 would be the same theta times R2. And so if I put these two ideas together, I would have theta 1 R1 here for L1 equals to alpha 1 initial length delta t plus the length, initial length. And then the second equation right here, L2, I would put theta R2 equals, and I would have alpha 2 initial length delta t plus the initial length. And they want me to find this angle in terms of the differences. So my clue here is to subtract the 2. And since 2 is bigger than 1, let me do this in reverse order. Let me subtract the top one from the bottom instead of the bottom one from the top. So this right here, factoring out a theta and going R2 minus R1. And then here, taking the bottom one and subtracting off the top one, the original length would go away. And these two would have the same common factor as initial length delta t. And then I would have alpha 2 minus alpha 1. And I think that gets me to the equation that says, okay, what is an equation for theta? I'll just bring the R2 minus the R1 over. And then this would be, and I'll write it alpha 2 minus alpha 1, original length, the delta t. I think that's what they were asking. Let's see. Derive an expression for the angle of bend theta as a function of the original length. Okay, got that. The average coefficient of linear expansion. I guess that's okay. This is actually the difference of their average linear expansion of coefficient, but I think that's it. The change in temperature, good, and the separation. So maybe to write them in terms of deltas, maybe this is a delta alpha, the difference between them, the initial length, a delta t, and a delta r. Maybe that's a better way to write it. And so that's our bending. In fact, let me jump to the solutions here.
I think that's correct. I think that's what they had.
You think that's correct?
Yeah.
Good, because mine's a little slow loading here. Oh, there it goes. Okay, and then 40 has a, yeah, they got that, and they got that, and they got that, and they got a delta. Yeah, good. Now, I know you said you could do the other ones, but maybe for others, or really maybe for me, I'm curious here. It says, what does B say? It says, show that the angle of bending decreases to 0 when delta t decreases to 0, and when the two average coefficients of expansions become equal. Okay. So physically what they're saying is if there's no temperature difference, we should be back to here, which means that, essentially we're looking at no angle between these lines. And that's pretty easy. You can just see, you put a delta t of 0 right there, you get 0 angle. Yeah. The other one is they're saying that the alpha, and actually I find that one more interesting. If the alphas are the same, you still get a 0. And that makes sense because if the alpha was the same, these two would grow the same amount. And so they would still just be parallel to each other. There would be no bending to them. They would each grow by the same amount. They would be longer, but there would be no bending, no arc to it. And of course, you can see that in the math here too, that if the difference between them, or if they're the same, I should say, the difference between them would be 0, and so you'd get no angle to it, no matter how much you warmed it or decreased it. Yeah, so I like that second part of B a lot. And then, oh, here's a good one. Yeah, see, I'm glad I read it. It says, what would happen if it cooled? And I would just say there's really not much difference in my thinking other than coming back to this equation. This is how much it changes in length. And you can have a negative or a decrease in the temperature. So the objects, which in this case, number 2, that got bigger when you warmed it, well, the one that will get the smallest when you cool it, it's the one that changes the most. And so what's going to end up happening is L2 is now going to be the smaller one. And L1 becomes the longer one. And so you get exactly the same thing. You get exactly the same mathematics. So you're going to get exactly the same formula for the angle. It's just going to be an angle on the other side. I suppose you could even argue that let's just use the same equation. And if we have a delta t that's negative, that will then give us an angle that is negative. And so that would just tell us it's on the other side. So positive angles means it bends, what do you want to call that? Concave left. And negative angles would mean it bends concave right. So yeah, that's a real good one, forcing you to think about. Yeah, I like that. That's pretty neat. What if it's cooled? But for that matter, I would say that could be extended because it's giving you the same thing as if you warmed it, but if you had switched the alphas. And so you put the one with the bigger expansion coefficient on the outside. I mean, if I would have just said that, the one with the bigger expansion on the outside, then the inside would have curved the other way. And so again, we could use the same formula for that. And so this formula, pluses if it would bend concave left, negative if it's concave right. So it's one of these kind of nice formulas that work out where it works both left and right, and you can use the same equation, and the pluses and the minus kind of help. D, show that a compact spiral biometric strip, in a home thermometer. So if theta is interpreted as the angle of additional bending caused by the change in temperature, the equation from part A applies as well. Okay, so they're saying we can use our equation in A. The inner end of the spiral is fixed and the outer is free to move. Assume that the material, the metals are bronze and invariant. Invariant. Very common metal used because it doesn't expand much. That's why it's called invariant. Like a nickel, steel, or iron alloy, something like that. I think we're going to have to look that up. The thickness of the strip is 2 delta R, 0.5 millimeters, and the overall length of the spiral is 20 centimeters. Find the angle with which the free end of the strip turns when the temperature is changed by 1 degree. The free, and then they go on. So I like this problem. They're trying to help you out by understanding a common engineering application for this. And they show a picture I see down here. Okay. I don't know if you can really see it in the picture, so maybe I'll help draw it for you. But these things are kind of nice. They're made out of a bimetal strip that's in a spiral. They look something like this. And in our case, they're saying that this original length is 20 centimeters. And then mounted on it, they put a glass cylinder where embedded in this glass cylinder is usually a metal wire that goes almost to the end and then a little gap. And then they put a little blob of mercury. Now, mercury is a metal that it conducts. And the idea then is if this expands, and the way I set it up, if it expands so it gets warm, this whole thing's going to tilt sideways. The mercury is going to roll down and make contact. And so maybe this metal piece is connected to the switch of an air conditioner, so that when it gets to be a certain temperature, this arcs over, the mercury rolls down and makes contact and turns on the air conditioner. And then as the air conditioner continues to cool the room, this would contract. And as it contracts, it would bend this cylinder back over, and the mercury eventually will flow back over here, breaking the connection and turning off the air conditioner. So that's kind of a low-tech, easy way to turn something on and off based upon its temperature. And as I look at the picture, it looks like they've got a thermostat. You can just see the coils there and the mercury glass tube. But unless you know what you're looking at, I don't think that black and white picture is going to really stand out to you. So anyways, I thought I would explain it. Anyways, let me actually do the numbers then, because the initial length we know, they're saying in this problem, take delta T to be 1 centimeter. And they say take delta R to be, and I'll put the 1/2 on the other side, 0.500 millimeters. Let me get these in the same units. Let's see, half of 0.5 is 0.25 millimeters, which would be 0.025 centimeters. All right, so there's my delta R. So to answer this question, I need to come back here and go, okay, the angle it moves, theta, would be this difference in their expansion coefficients. So I'm going to need to look those up here in a second. The length of it is, what would I say up here? 20 centimeters. The delta T, let me just double check. Did I read one here? Find the angle through which the free end of the strip turns when the temperature changes by 1 degree Celsius. Okay. And then the delta R is the 0.025 centimeters. And that's why I wanted to make sure I got those into the same units here. So my centimeters would cancel off. Oh, now I need to look these up. And so let me just make a note to myself before I go to the textbook or Google. I'll decide which one to go here. What do I have? I have brass for one of them, or was it bronze? Oh, it's bronze. Okay, so bronze is one of them, and Invar is the other. Okay, so let me find the textbook here. Good question. How do I get to my desktop? Aha! And let me open up the textbook. We go chapter 19. Okay, good. Let me scroll. And somewhere in here, I think here it is, table 1. They list all these. All right. So brass and bronze are 19 times 10 to the negative 6 in units of inverse degree Celsius. Oops, no close parentheses. And that's a pretty big number. Brass and bronze, that's one of their challenges as a metal. They change quite a bit when you heat them and cool them. Not as much as aluminum. but far more than still. And then the other one, the invar is the common one used when you don't want something to change by too much. It's a nickel iron alloy. And so it's a 0.9 times 10 to the minus 6. Oh, and if anybody cares, I guess I should check. I would assume that these same numbers are listed in the OpenStax book, but it doesn't really matter where you get them. OpenStax, Survey, the internet. Okay. And well, let me just move the unit. So the unit would be this inverse degree Celsius. So then I have a 20 and I have a 1 degree Celsius. Uh-oh. Uh-oh. It froze. Ah. Okay. Let me turn my phone on again. All right. I'm back, guys. Okay, so now let's actually put in the numbers, but the inverse degree would change by the degree, and we're going to end up with just a real number here. So if I do this, if I go 19 and I subtract 0.9, 18.1, and multiply it by 1 times 10 to the negative 6. Okay. So that's this number here. Then I can multiply that by, it looks like a 20 and divide by 0.025. Divide by 0.025. And I get an angle of 0.014, I'll just call it a 5 radians. That's small enough that I think I'll like degrees here. So I'm going to go times 180 divided by pi, and an increase of not quite 1 degree, but about a 0.83. In fact, make me jump over here and check the solution here. What'd they get? Yeah, 0.83 degrees. Nice. Good. Nice. All right. Well, nobody's asking a question for that. So, all right. So hopefully that's good.
Yep. Thank you.
Sure. And yeah, I know you didn't ask about anything but A, but I was kind of curious. And it's just nice to put it on video. If you're asking part of it, I know there's a bunch of other people asking other parts of it too. So might as well keep going with that one. All right, so I'll say it again. If there's any of you 102 people out there, you got priority. All right, I don't see any, so I'll keep going. So that was 40. Then we got down to Hunter's question here. All right, can we go over number 9? Sure. 123, chapter 19, number 9, and I'll call this 1048. Okay. So chapter 19, number 9. Somebody, could have been you, Hunter, sent me a question on this last night, and I was hoping to have time this morning to do the solution on it, and I did, and then I go, well, maybe we'll get to it in the Zoom today here. So, all right, good. So let's do this one here. Let's see. So I need to look at the question. back to the question. Scroll up to number 9. Yes. Putting things together. Great engineering technique here. Very common here. But it says here a thin brass ring with an inner diameter of 10 centimeters at 20 degrees. All right. So I'm going to start off here and say, okay, I have a piece of brass. It's a ring. So maybe it looks something like this. The important idea, though, of the ring here is to know that its inner diameter is exactly 10 centimeters. It is inner diameter of 10.00 centimeters. Okay. And it's also important that we tell what temperature it is. That was a big part of this lesson, and actually the last problem we did, and probably many of the problems we'll do here in this chapter, is how big are these things? And since they change with temperature, we can't really say what size they are without specifying also what temperature they are. And so that's kind of the new lesson here to learn, is that temperature needs to be stated with length. It doesn't make any sense to say what its length is without also saying its temperature if it's in the process of changing. Now, it doesn't change by much. So that's why, all the way through 121, we never bothered to say the length and the temperature together. But if you're talking about small differences and it can matter, then you got to say it's temperature. All right, so I'll say it again. So the inner diameter is 10 centimeters, at least to 4 significant figures, it's 10 centimeters at 20 degrees. It is warmed. All right, so that means it's going to get bigger. And not only does the metal get bigger, but since the metal makes the hole itself, you're essentially saying the circumference is getting bigger. So I think one of the things to realize, it can be a little challenging, is that holes in your objects get bigger when you warm them up. They don't get smaller. The hole is actually dictated by the material around it. So, if my fingers represent the hole around it, then when they get bigger, the hole gets bigger. And that's a little hard to digest, I think, because people kind of want to see the material move inward, not the circumference get bigger, but the material move inward and make the hole smaller. So keep in mind that as we warm it here, the hole is going to get bigger. And so they're saying it's warmed and it's slipped over an aluminum rod of diameter. Okay, so now I'm going to make an aluminum rod. Here's a rod. And it's made out of aluminum. And it has a diameter. And so we want to try and get this ring over this aluminum diameter. And the diameter is a little big. It's 10.01 centimeters. And again, at 20 degrees Celsius. So we can give it size, but we also have to say what temperature. And so clearly at 20 degrees, this isn't going to fit. There's going to be a little bit of bumping going on. The brass, just won't quite work. Here's the rod and here's the brass, just like it just doesn't fit. It's the opening here of the ring is just not quite enough. All right. It says assume that the average coefficient of linear expansion is constant. To what temperature must this combined be cooled in order to separate the parts? Now, this is interesting because they say separate them, and I kind of drew them as if you can't even get them together. So keep in mind that they've already been put together, okay? So probably what happened is this. This is a common way of hooking things together, is you take and you make the brass ring, and as you can see, the inner diameter is a little too small for this rod. But what you do is then you put this rod in a hot environment.
The ring or the rod?
The ring, yeah, the ring. You put the ring in a hot environment, it gets big enough, then you can slip it over the rod, then you let it cool down to room temperature, and it grabs hold and it's compressed on there. And that way you don't have to use any glue, you don't have to drill any holes to put a nut and a bolt or a rivet. And because the putting a hole in it to put a nut or a bolt can actually weaken it. So this could actually be a stronger connection than a weld, than a rivet, than a nut and a bolt. So this is used a lot, not all the time. It's a bit of a challenge in the manufacturing process. So, but where it can be useful, it's irreplaceable. So anyways, and maybe I explained that in the lecture video, because there's a story I usually like to give about, and I don't know if they're still in town, but they used to be in Santa Barbara, and they manufactured the axles for the Abram tanks. And this is how they built it. And they would come in and they would cool this down, or I guess warm this up and cool this down and put them together, and then they would be under tension. And they were able to get some incredibly strong connections with lighter weight. And of course, that's why they got the contract to build the axles, and they were a very successful company here in town. And then their first real test happened. Well, I guess it's a long time ago now, but it was Gulf War I, so 1990, when the Army was asked to get in their tanks, drive 1,000 miles of open desert in their tanks, and come around behind the Iraqis, and it was just considered impossible to do. Which is why the Iraqis left the whole desert open and defenseless, and that's why. But this was a big test and a big question. Would these axles hold up? Could they handle the stress? Could they make 1,000 miles? Blah, 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 blah. And they worked really well. So so back to this problem. So this problem was one where we're going to say they're already together, and now we want to try to get them apart. And what's important to realize then is, to get them apart, you would want to cool it down, because the expansion of aluminum, or the contraction of aluminum in this case, is a bigger number than the brass. And so as you cool them down, this is going to start to get smaller at a faster pace than that one. And eventually they may get the same size, and now they can just slip right off each other. So that's the idea. We want the two diameters to be the same, okay? And we can do that by cooling them. But the other thing to realize is they're already hooked together, so you have to cool them together. You can't cool one over the other. All right, so let me do this. Let me write an equation that would represent the diameter of this brass one. And so I'll go L sub B, how about that, for the length of brass. And my length is going to be the diameter of this brass, because it would be the original diameter plus alpha times its original length times delta T. And I should have put a little B here for brass.
Just real quick, we're talking about the inner diameter, right?
Yeah, thank you.
Okay, cool.
Yeah. I'm not even going to pay attention to the outer diameter. So this is the diameter. And of course, you can see that if delta T is under 20, so this is the 10 centimeters is the length of 20, that's a negative number. And so the diameter here starts to get smaller and smaller and smaller. And that's where I'm going to have to go with this. I'm going to have to get a negative temperature. But I'm sure the math will tell me that. Now, let me do the same thing with the diameter of the aluminum rod. And so I'll go length of aluminum. And the length of the aluminum is 10.01 plus alpha of aluminum. Its original length, 10.01 times delta And I said it earlier, but haven't looked it up, that I know that the coefficient of expansion of aluminum is a little more than brass, partly because the last problem, I was just looking at it and said, yeah, brass changes a lot, but aluminum changes even more. Both of these change a lot with temperature. Okay, so now if I want them, to slip off, I guess I'm really saying that at what temperature do they have that same diameter? And then if I go maybe just a hair colder than that, it should slip right off. So I'm going to set these two equal to each other. So the brass would be 10.00 plus alpha of brass times the original 10 delta T. And the aluminum then is the 10.01 plus the alpha of the aluminum, its original length, 10.01 delta T. And now if I go to solve this for delta T, let's see what I get. Maybe I'll just move this 10 over to here, so that becomes 0.01. And then I'll move this alpha over here. Well, maybe I'll write it as alpha of brass times 10 with the delta T, but I'm going to factor that out, minus alpha of my aluminum times 10.01 delta T. Or finally, getting something to work with, delta T would be 0.01 over, and I'll just put the number first, 10.00 alpha of brass minus 10.01 alpha of aluminum. And so here's where a calculator, and for that matter, the textbook are going to come into play here. Let me clean up my screen here a minute. Pretty nasty looking. All right. Okay, so back to the textbook here. So let me go 10 times the alpha for brass. And that would be 19 times 10 to the negative 6. Okay, then let me subtract off 10.01 times the alpha for the aluminum. So that would be 24 times 10 to the negative 6. And hopefully that's a negative number. Okay, good, it is. So 0.01 divided by that number in the denominator gives me a decreased temperature of negative 199 degrees Celsius. So I got to get it real cold to get these apart. So these are stuck together really well. Can they come apart? Sure, but you got to, we're looking like you got to put it in a bath of like liquid nitrogen before you get that cold.
And you would actually have to get it just like a hair colder too, right? Because at that point, the diameter is equal.
Yeah.
Mm-hmm. Okay.
I suppose they're exactly. Now, I thought I saw a little more to this question. Let's see.
Mm-hmm. Yeah.
B. Wait. Explain whether the separation is obtainable. So yeah, the separation is obtainable. Not easy, but obtainable. Put it in a liquid nitrogen bath. Then not unreasonable. But this one says, what if the aluminum rod instead was 10.02? See, at some point, the diameter is going to require such a cooling down that we can't get it any colder. It's not just because of technology, but because of the physical world only gets so cold. There's an absolute zero. So I have a feeling that, look how far down I had to go here. I had to go down 220 degrees. So I probably have to do another 220 degrees, which is beyond the negative 273 that is even possible. So I'm not thinking it's possible. However, let me run the numbers here. So what would be different in this problem for B would be right here. This would be a 10.02, which would translate to 10.02 there, which would translate then, and I guess here also 10.02 there. So there'd be two places. So 10.02 there. And so down here at the bottom, this would become 0.02. And that's why, in my mind, I'm thinking this is going to be about twice as much cooling. But there is a small effect here too. So 10.02 would go there. So it's not quite a linear function, but approximately a linear function. Because when you take 10.01 and changed it to 10.02, you really didn't change much. But you changed this one dramatically. You changed that one by a factor of 2. All right. So yeah, I don't think this is even possible. But let's go up to that original equation I had and re-enter it. I think, let me just go to the beginning. I think that's the only thing I needed to edit, because the first one down here would be 10 times 19 times 10 to the minus 6 minus 10.02 times 10 to the 24 times 10 to the minus 6. So there's the denominator. Yeah, and you can see it barely changed. Look at that. It's still really a negative 5, and it barely changed. But now it would be 0.02 divided by that last answer. And we're looking at a temperature of negative 396. Oh, I would have expected a little over 400, but maybe that had a bigger effect than I thought. Anyways, but assuming I did that number right, either way, it is colder than you can get. You can't get this cold. So no, if you put them together with that diameter, of course you'd have a hard time, but it could be possible. You'd have to warm up the brass pretty good, but you could probably warm up the brass and cool down the aluminum and put them together. Then when they warmed up the room temperature, if the stress wasn't enough to crack the brass, this would be a good connection, because there's no way you're getting them apart ever again. You just have to throw the whole thing into a really hot bath and melt them, and then the aluminum floats to the top because it's lighter, and the copper. Well, brass is what? Copper and zinc. So the copper, and I'm not sure which. I think copper has a greater density. Yeah. So the copper would go to the bottom, the zinc would be in the middle, and the aluminum would be up at top, and you can separate them. I think that's right. No. I only say that because I don't know if you've ever tried this. It's kind of fun with pennies to put a penny on a hot plate, because they got a lot of zinc in them, and then the zinc rises to the surface, and now it looks like a silver coin. Yeah.
So I have a conceptual question there. So so far, I think we've worked with a lot of metals and stuff like that.
Oh,
Do we witness like thermal contraction and expansion with like ceramics or like organic materials as well, or is that something that we can't really calculate quite yet?
Yeah. No. Great question. Metals do it the most. So they're the most significant. This is for a first class on expansion and thermodynamics, metals are the place to deal with, and they're they change quite a bit, so they're really problematic.
Mhm.
So here's some very interesting pieces. If you take a simple model and just say, okay, it's made out of atoms, and when you warm it up, the atoms move faster, they're going to bump harder and they're going to expand. That simple model itself says everything's going to get bigger. And so do ceramics get bigger? Yes. But it's a very, very small amount. Does glass get bigger? Yes, but a very, very small amount. So when you mount a glass window, particularly a very big glass window, you need to take this into consideration, and you need to put like some kind of rubber seal around it that can be used in the expansion. Otherwise, if you just mounted it in cement or metal, it would crack the glass. So yeah, everything does it. Now, here's where things get more complicated and very interesting. You said organic materials. Oh, yes. However, we don't usually talk about the organic materials because if you warm them enough that they start bumping hard, they break apart and they don't become, they're not organic materials anymore.
Yeah, they decompose. Yeah.
Yeah, this is like saying, and we'll say the same thing in the next chapter. We'll say that everything has these 4 phases of nature, and if it starts as a solid and you warm it up, it becomes a liquid. But you got to be a little careful with that. Something that is organic, has this huge, long macromolecule. And the truth is, if you take like a piece of chicken and you warm it up, you don't get liquid chicken. You get burnt chicken. What happens is long before you can make the molecules break apart from each other, you break the individual molecule. You just don't have chicken anymore. So there's no such thing as chicken in the liquid state. Same thing with a carrot. You don't get liquid carrot. You don't make tomato soup by taking tomatoes and heating them until they turn to a liquid. You just get burnt tomatoes. All right. So I'm being kind of silly, but I hope you see my point that it can get kind of complicated here. But yes, the general answer is when you warm something up, the molecules move faster. It doesn't matter whether it's a metal, a glass, a ceramic, organic material, it gets bigger. Actually, some of the funnest ones I like to talk about is these carbon fibers. Because carbon fibers actually take a long link of carbon, kind of in the shape of an S, and another long link of carbon. And so if you can imagine a bunch of S hooks kind of hooked together, so you got an S hook connected to another S hook, connected to another S hook, connected to another S hook. And if you heat them up and start shaking them, they actually look more like this. They bounce off each other, and the chain actually gets smaller. They don't get bigger, they get smaller. So carbon fiber is a very interesting fiber in the sense that if you make a plane out of it and you fly the plane and the air friction rubs on it, the skin of the plane actually shrinks in and compresses the plane. And so like all these planes that are made out of these carbon fibers these days, or even these fancy bikes that are made out of carbon fiber, they actually get under a lot of stress when it gets hot. And anyways, it's part of the overall engineering you got to think about, but it's fascinating.
Yeah, thanks for going over that. I enjoyed that.
Okay, good. All right, so let's see. Let's move on to my Zoom here. All right. So Dylan comes next here. Can we cover a 120 problem? Yes, we can. Dylan, what would you like?
It's a question from the homework
Okay.
Would it be easiest to share my screen?
Let me just ask you, I maybe not, because I called up the homework. Can you tell me what the title is?
Yeah, one second. It's 2D motion.
Okay, so it says 2D motion. I got that page, okay?
And
then it said-
then the one I want is the one where it says Valeria runs. It's the third problem down.
Third one down, velocity vector function, that one?
Yes.
Okay,
And so specifically my problem is solving for like acceleration vector magnitude.
good, okay. Let me go through this. Let me just write this down. Velocity vector function. Velocity vector function. I'll put in my notes, VVF. From 121 at 11:15.
Also, I
Okay.
guess just before we start,
Yeah.
what do you suggest for when you come across a problem that you just don't really know what to do and you kind of get stuck? Like,
Oh, well, is it, you say you don't know what to do.
like for me, like it's like I'm not sure like which equation to use, or I don't know, just
Okay.
stuff like that.
I guess my first part of it would be this. I mean, why don't I try to explain my thinking as I read it? Okay. I mean,
Okay.
I would do this. So I got the problem and I read this first one. It says, Valerie runs around a circular track, comma. Now circular track. Part of this section was things moving in a circle. In fact, this section was probably divided into two pieces: projectile motion and circular motion. Okay, so I guess the first thing I would do is say, okay, what do I remember about circular motion? And and if the answer is nothing, maybe it's time to go back and look at examples that were done for me. And I say for you, I was about to say in the textbook, but oh, you do have a textbook. Yeah. Wait.
Mhm.
So you have to. So I'd go back and look at that textbook and look at all those pieces that have the circular motion. And if I did that, I would probably come across something like this. There was something that said the radial acceleration is v squared over r. Okay, so that's the part that's pulling the person inward. But as I read it, I would say, okay, then there is a tangential acceleration. And that is, as I go back and read it, the change in speed versus the time. And then as I read it, I realize that they're trying to say that those two things are at right angles. So I'm kind of hoping that that would be a clue in my brain to go all the way back to chapter 2 on vectors. See, because on vectors, we said if you had, something that was like pointed at an angle, it would have components. And of course, when we did chapter 2, we called this its x component and its y component. But as I kind of look at their circular motion, I'm thinking, wait a minute, they're really saying, think about the x as being the r, and think of the tangent as being the y. So what they're really saying is these are my components of it.
Yeah.
All right. So again, one of the things I learned back in chapter 2, or maybe I'm still learning back in chapter 2, is that if this is the x component and I take the x component and I square it, and I take the y component and I square it, I get the total length of it. Let me call it the hypotenuse, c, and square it. Okay, so it's, I guess, I'm trying to I guess what I'm really trying to say is there's not really one way to answer your question about, how do you approach a problem other than to say you do have to have some background information, and the reading of the problem should clue you that way. And then now it relies on you saying, okay, how much do I remember from the reading and how much do I not remember? So, usually I would say this: students read the circular motion and they probably forget the tangential one because that's new. They usually remember the radial one because that's often covered in a physics 102 level. Then they usually remember that vectors and their components because they did that 2 weeks ago in chapter 2. So that's kind of settling in. So I'm just guessing, and every individual is different, but when I read that circular motion, these are the 3 things that I instantly want to know or need to go back and re-study them before I can move on with the problem.
Okay.
Okay. So, and I'll just say right now, I've only read the first, 1, 2, 3, 4, 5 words. Just says Valerina runs around a circular track. And so I'm just saying, okay, now what do I know about things going in a circle? So I have forgotten I shouldn't say forgotten. I have not considered the projectile stuff. I was just like, okay, I'm not worried about the projectile stuff. I'm worried about the circular stuff.
Yeah.
And then part of that is I'm also have to worry about vectors. All right. So that's kind of, I guess, my first comment. That's what I would do first in my brain. Okay, is get that. All right, now let me keep reading. So then it says, starting at the time t equals to 0, okay, her velocity vector components are described by the following function. Okay, so at this point, maybe nothing new other than, all right, they're giving me components. So again, I'm thinking vectors. But I have this equation. I have a 5 plus a acceleration, which they say is a negative 105 t. Okay. So I guess that is saying she's slowing down because it's a negative acceleration, at least in the x direction. Oops, it goes off the screen. Sorry. Okay. Now the other equation is her y component. Okay, so again, my brain right now is thinking, okay, I got a lot of vectors, and I'll tell you this too. I'm also kind of struggling in my mind about, okay, which one is radial, which is tangential, or do I know? I don't know how the circular path is laid out. So I in my mind, I'm still kind of going, okay, is the x the radial, which would make the y tangential, or is it the other way around? Or maybe some combination. I really don't know at this point. So I'm still reading, still thinking. Okay, but I'm just going to write this down. All right, so her y component is 2.09. Is there a t in here? Yeah, t. Okay, so that's the second sentence. Okay. All right. Now let me keep going. At time 3 seconds, okay, the magnitude of her displacement vector d and the magnitude of her acceleration vector is a. Okay, I don't see much information about a circle yet.
Yeah,
So
I
I thi-
didn't really understand, like, it didn't seem
Yeah.
like that was very crucial information
Um,
by the end of reading the question.
um,
But like, so my biggest
But-
problem was, assuming I did it correctly, is
mhm.
that, so I took the initial velocity of x and then the velocity of y,
Uh-huh,
and then I took the integral of those components
uh-huh.
to get the position functions for x and y. But then when you do the same in the other direction, you take the derivative of x and y of velocities, you are left with just the acceleration vectors.
Yeah.
But then I was confused as to how you plug in the t equals 3 seconds part, because then the t variables have disappeared.
Oh, okay, exactly. So that's how can I say this concisely? Yeah, so you did it right. There just is no time variable. What you basically discovered by taking the derivative, and I apologize. I made it longer than it needed to be. I didn't see this coming. I was so busy thinking about the things I knew about a circle, but as you're pointing out, that wasn't necessary. But maybe that was good for you to
It's
see
it's fine. Yeah, no, it was good.
because I didn't need it. All I needed, and I'll do the acceleration first since you're asking about that. As you said, to get the acceleration vector, you take the derivative of it. Okay.
Mhm.
I don't even think you need to take the derivative because whether you take the derivative or just go back to the reading said this is the acceleration in the x direction. I mean, it just said 1 point or negative 1.05.
Yeah.
But if you took the derivative, that's fine. And the same thing with the acceleration in the y direction. Uh, you don't need to take the derivative. They just tell you that the acceleration is 2.09.
Yeah.
Okay. So if you take the derivative, fine. If you get it from the reading, that's fine. But the real step to this, and you did it right, has to do with uh, chapter 2 on vectors, that you get the magnitude of it by taking the x component and squaring it, and then the y component and squaring it, and then take the square root. So we would have the x component squared, we would have the y component squared, and we would take the square root. And that's what you did. I think what's bothering you is you said there's no time in there, and that's fine. That just means this is your acceleration, and it is a constant in time. In other words, if I told you the time was 3 seconds, you would do the same thing as if I told you it was 7 seconds.
Because the acceleration would still be the same because it's
Uh-huh.
constant.
Yeah.
Okay, that makes sense.
And of course, you can totally see it back here where you have, this statement of what the acceleration is. You notice it doesn't have any time in it.
And then, so for the position vector, though, it is important to plug in the time. And then,
Yeah.
okay.
So for the position, you would get it. Yeah. But
So I guess my other question, if I could ask it, is, what do you like? I think for the last problem before this, you were given components and then you were supposed to find a kinematic equation. So like you would essentially turn the velocity functions into some variable with respect to time. And I'm a little confused on that, like on problems like that where you're given information and you're supposed to set up an equation with the t variable in it.
yeah,
I might be mistaken, but
no, forgive me. I'm a little bothered more on this question. There's no real circular part coming out of it. But let me not. Yeah, there's. I feel like I'm missing something because it says it's a circle. But I think you're okay. Oh, anyways, I'm sorry. So I got sidetracked on that, and I also disconnected my phone here. Let me stop that. Ah. Now I really messed things up. Let me see what it does here in a second. And I'm sorry, go back, say that again. What was, you said something about the time?
So for the other, I think the problem before that, where it's the insect flying with the velocity vector.
Yeah,
So you're given the initial velocity of X and Y,
yeah,
but then you're supposed to set it up into an equation with relation to the time variable.
yeah.
But I'm a little confused for problems like that, where you're given information and then you have to put it into an equation with respect to t. Is there any tips you could give me for problems like that?
It's tough to like give a recipe and say, hey, do this, and do this, because what you do really depends on what is given in the problem.
Yeah.
Okay, so that's why practicing problems is such an important part of the learning here, where you have to sit down and say, okay, I'm going to do this problem. And eventually, when you do all these problems, you begin to realize they're the same thing. All I have to do is look at the X component and the Y component. The way I would describe these two problems that you just referenced is the one we were doing, and my phone has gone crazy now. And I wish I could figure out what's going on here. I'm going to try it again. But the one we were doing together, see, they gave me the components and I was after the magnitude.
Yeah.
Okay. Whereas the one above it with the flying insects here, they gave me, well, they gave me the components for the acceleration. Then by integrating that, I would get the components for velocity. Then by integrating that, I would get components of position. So in a sense, I would say these are kind of the same problem. You're going, in this case, from acceleration, and you integrated twice, whereas the problem below it, we had velocity and we went either direction. We went first a derivative to get acceleration, and then an integration to get position.
Yeah.
But probably the big thing is at the end of the problem for the insect one is you've got a distance where it says it's 30 degrees. So they've given you magnitude and you have to go back and find components. And so it kind of depends on the problem. So the insect one, they're ultimately giving you magnitude and you got to get components. Whereas the one we're doing now with the runner has components and you're asked for magnitude.
Yeah.
And I guess what I'm trying to say in this is really the same problem. It looks a little different because if you have components and you're asked to go to magnitude, that might look different than if you have magnitude and you're asked to go to components. But that's why I'm trying to say is there is no one recipe because it depends what information they give you. It's kind of like, you're solving a puzzle and they give you the right-hand side, so you got to solve the left. But if they give you the left, then you have to solve for the right.
Yeah.
And hopefully it kind of looks like the same puzzle to you.
Yeah, I don't know. Like, it seems like I get like almost like hyper focused on like one area, and then it's like I feel like I've hit a wall, and then it's hard to kind of change my perspective and then see it a little bit different, Like, how, is there any tips to like kind of get out of that like headspace, I guess?
I guess I would say make sure you try to get the big picture where, you know, it's not the individual details, it's the projectile motion, and projectile motion, or two-dimensional motion, excuse me, has components. And if they give you components, then you work towards magnitude. But if they give you magnitude, you work towards components.
Okay.
Maybe another big picture is the connection between position, velocity, and acceleration. See, that insect problem, if I'm reading it right, and I haven't done it completely, but if they gave me acceleration and I wanted to get velocity, I would do an integration. And then to get position, I would do another integration. But the problem we were doing with Valerie running in a circle, we already had the equation for velocity. So I went ahead and said, why don't you take the derivative to get acceleration, but yet do the integral to get position? And I guess I'm trying to get you to see kind of in the big picture that those are really the same type of problems. That there is a connection mathematically between position, velocity, and acceleration. And don't think of it as, oh, I do integrals, and this type of problem I do derivatives. Oh, I messed that up. We were given velocity and we asked for derivative, but then we had to get acceleration, so we went this route. But we could have been given position and we would have to do a derivative. And so I don't know if this is very helpful, but I guess I'm just trying to say, if you see this big picture, these two problems hopefully look the same.
Yeah.
Because they gave me acceleration and I needed to get to position, so I integrated. But if they gave me position and I needed to get to acceleration, I would just differentiate.
Yeah.
And if
I
you
guess
can
my solution is just doing more problems. So I see the pattern.
Yeah, and I'm sorry, I can't really give you a good solid answer. This is what you do every time. But I think the best thing to do, and this is why I like to just work out problem for a student, is to say, okay, let's do problem number 7 together, you know, and say, all right, what are you going to do on number 7? Knowing that problem number 8 is going to be a little different.
Yeah. Well,
but,
so like my solution, or not my solution, but my approach has been, and what I've kind of changed this semester as compared to others, is what I used to do was I would just read through the textbook, but now I've challenged myself to, as I read, I do the example problems. So,
oh, good.
But I don't know, it's really time consuming in my experience. And I mean, I could definitely put in more hours, but I feel like I put in a lot of time to just read through them and then do the problems. And then I do the homework. And then so what my approach was today, since we have that reading quiz on Fridays, is I wanted to try to go through the homework and then do them again. And this week, what I noticed was that the projectile motion problems and just even the first problems that we're doing currently, those were giving me a lot of issues. And then the centripetal acceleration and tangential acceleration problems at the end were actually pretty easy. So I don't know. I guess I'm trying to prepare for the quiz, but I don't know. I don't feel very prepared, I guess. I don't know.
Yeah, don't feel lonely, Dylan. It's interesting. It's like the math is not complicated. The physics aren't complicated, but it's figuring out how to mesh the two together that seems to be the challenge.
Yeah.
For me, at least.
Yeah. No, for me too, for sure.
Yeah. No, I see that. The applied physics is, you know, when you apply it, I've often described the physics 121 this way, that the physics is about like the same physics you learned in your 102. Mm-hmm. But you're asked to take that and integrate it with the math you learned in your 150 class.
Mhm.
And that's where the challenge really is. You're not learning any new math, you're not really learning any new physics, but you're putting them together so you can do closer to real world problems, and that becomes hard.
Right.
Yeah. And then that's where practice comes in. I like to say this when it comes to studying, Dylan, see if this helps. If you have a chapter to read, I like to say, read the first chapter just all the way through. Okay. Don't stop and try to do the formulas and the examples yet. That's an important phrase there. Yet, because you don't. I don't want this to take too much time, because what I want you to get out of the first reading is the gist of the chapter. And that way, then go back and read it a second time. And the second time, read it slowly. And the second time, work through every example. And that really gives you this benefit of knowing kind of where they're going with this, because you've already read it through the first time. And by reading it through the first time, you kind of are seeing where they're headed. And that really gives you some insight then of, okay, I see why they're explaining it this way, because I know on the next page they're going to do such and such. I didn't understand it the first time I read it, but at least I know where they're headed.
Yeah.
And
Okay.
because it can take a long time, I find that reading it first very quickly actually helps. Then when I go back and read it slowly and detail oriented.
Okay. I think I'll try that. I think that'll help.
And another thing that has helped is sometimes I will go and after reading it through the first time, also go and read the homework questions.
Yeah, I
So-
think that was also
so-
a mistake I made too, as I read through all of it and then I went back to the homework and then it was like the centripetal acceleration was all fresh because that was at the end. So those were the easiest, but then everything else was kind of jumbled information. It was difficult.
Right. So I found that if I read the chapter really quick, even though, to be honest, I probably only learn about 10-20% of the material, but it doesn't take long either. And then when I read the homework questions, even then I read them quickly and I go, "Guy, that didn't make sense." But when I go back then and read the textbook slowly a second time and do all the examples, I'll be working through the example going, "Oh yeah, this was just like homework number 4." And I'll even put a little mark in my margin. This is like number 4. And sometimes I'll even flip back and reread homework question number 4 and 5 and go, "Yeah, this was like 4 and 5." And so
Yeah.
as I read it, then when I get to the homework later on and I read it, I can flip back to that margin and say, "Yeah, it's just like this one." And so I can flip back and forth from the homework problem that I'm struggling with and the little notes I made myself during my detailed reading.
Yeah, I like that because
And it,
as soon as you get exposed to it, you're like even your subconscious brain is kind of thinking about it,
yeah,
working it out.
yeah, it's amazing what the subconscious brain does. That's a good way of putting it. But it's just
Yeah.
also, I don't know. Yeah, there's just something in the mind that says, okay, now I kind of understand why we're doing what we're doing.
Yeah, I,
And so
I
that,
kind of think of it like a child when they're like all of a sudden one day they can talk, but like
Yeah.
before that, their subconscious is just figuring everything out. And so I think that's a tool that we use throughout our lives. But
Yeah.
as we get conscious and aware of, speaking and thoughts and stuff, it seems to not be as much of a thing we consider. But I think it definitely like still works that way for physics or whatever you're doing.
good.
Yeah.
Good. And I'll say it again, it's not easy, but if there's somehow you can, get yourself to kind of see the big picture. And believe it or not, I would kind of explain that this little diagram, which is kind of messy here, maybe I'll try it again here, position, velocity, and acceleration is really what kind of summarizes every problem in this 2D motion. that
Yeah.
you're just going to say, all right, how do I go from acceleration to velocity? I integrate. Or the other way around. How do I go from velocity to acceleration? I take the derivative. And now, if I have two-dimension motion, this means I just need to do it once for the X and once for the Y.
Yeah.
And then if they ask me, something about X and Y and total, I have to remember that the components together make the total using Pythagorean's theorem. And so sometimes they give me the magnitude and I got to figure out components from it. And other times they give me components and I got to figure out magnitude from it. So it's kind of this, that's kind of my big picture of this chapter.
2D motion. Yeah.
Uh-huh. So this twice, because this is for X and for Y. I know I only put X here, but I was thinking it's
Mhm.
also for Y.
Yeah, definitely.
Now, to be
Alright.
honest, I'm still a little shaken up back here of the one we did, because I totally went down this road when I first read it about a circular track, and I started thinking about radial and tangential, and that never entered in here.
Yeah,
So,
I don't know why it was written like that. That was kind of weird. But
oh, I said circular. It actually says curved track. So maybe that was my mistake.
well, I mean, either way, right? It would still have some centripetal force that's causing you to turn.
Yeah.
But I mean, it didn't seem like the question ever got that specific.
No, it didn't. So I think because if you look at this, the numbers they gave you, they're having the X component slow down while the vertical component speeds up. So it's kind of like the first quarter of a turn, where first quarter of a turn you would be losing your horizontal speed and gaining in your vertical speed. So we didn't have to do anything with it because it was already kind of buried in that equation. So
Yeah.
in theory, that was supposed to be easier for us. But in practice, because I read circle instead of curve, it threw me off. Yeah.
Well, I mean, I had to do more with my question too. So
Okay. Good.
like my question before. But yeah, thank you.
Uh-huh. All right. Well, um, let me jump back over here to the Zoom. And oh, that's the last one in the chat box. Oh, and it's break time. Oh, it's past break time. Wait. What time do we break? 10 to 11:30. Yeah. Okay. All right, everybody. Well, if there's no more chat, we're in there, and this will be a good time to take our break. And from 11:30 to 12:30, I'll take a little break, stretch my legs, and see you guys back at 12:30. How's that?
Sounds good.
All
All right.
Thank you.
Bye.
All right. Bye.